Uy, that's my pinch down, huh? My fingers are.
Here. Excellent.
In your pocket?
In my pocket.
40-some people online. I don't know
Okay,
if the room's
wonderful.
there yet.
Oh,
48.
no, that's good. Let's go this way. Okay. Oh, can I drive?
Yes, you may.
Okay, so how do I do that? Just,
This
okay.
is it forward and
Okay.
backwards.
Excellent, okay. Thank you very much. Hello, everybody. My name is Shirley Dion. I will be presenting the GPM timeline inhibits for INT processing. Let me introduce myself. I'm a system safety engineer for ASRC, and I work at Goddard Space Flight Center and been supporting Goddard Space Flight Center for more than 27 years. My last mission was GPM, which launched February 27th from Tanegashima, Japan. Some of you might be wondering what a system safety engineer does. First of all, I work unmanned missions, and we work as part of the spacecraft development team from design through launch. We make sure that the spacecraft design, integration, and test process at Goddard and at the range minimize risk to personnel, safety, hardware, and the facilities. Our skill sets are similar to systems engineers, but our focus is different. Systems and design engineers ensure that the design works and they optimize performance, whereas system safety engineers look at the same design and ask the question, what can cause that design to fail? And if it fails, what happens next? And we look for ways to minimize risk. Ideally, you need both perspectives on a project. As part of this process, we develop safety assessment reports and hazard reports that are presented to the range prior to arrival, and we also hold safety reviews. Let's see, you said, okay, here we go. Okay, so this is the agenda for today. Basically, I'll be going over the creation of a tool, a system safety tool, some terms, a little bit about GPM, and also a four-step process that I use to create the tool. And in addition, we'll go over some hazard report controls and verifications for safety critical software. Okay, so let's go over the scope. Here we go. There we are. So as a safety engineer, the process to make sure we are safe during launch site integration and testing, and especially on the pad, are well defined for our programs. We have analysis tools defined by the range and also by NASA. So we write safety data packages and put together hazard reports and complete compliance matrices that are reviewed by the range, and we have multiple safety reviews. But for INT at our launch, at our INT center, we have considerable hazards to resolve as well. So that, for us, that was Goddard Space Flight Center. Yes, we need to complete documentation like operational hazard assessments, but no real safety review, no real hazard reports are developed. Most of us would agree that more emphasis is placed on assessing safety hazards at the range rather than at the integration and test site. Today, I'll be sharing one approach to capturing and understanding inhibits and controls during INT. Currently, this process is registered as a new NASA technology and is being evaluated for patentability. I developed this process tool while working on GPM. GPM, to me, was the most complicated INT operation I've ever had to analyze. Doing the typical operational hazard analysis did not seem to cover all the bases. So what I'd like everyone to get from this is the importance of tracking inhibits, that the inhibit configuration needs to be written down so that everyone can look at it together, and it needs to be done relatively early in the planning process to be effective. One benefit I did not consider when I started this assessment was how useful it would be talking to other engineers who might not be quite as open-minded about safety and making sure we have the right number of inhibits. And as an added factor, GPM had safety critical software, which I'll tell you more about as we go along. Okay. Okay, so originally, GPM had all of its electrical safety inhibits designed into one electronics box which was called the SIU, or Safety Inhibit Unit. In flight, the box, when it became powered, would then power up after flight separation. This design allowed the system to be very safe from inadvertent deployment or turn on for RF transmitters. But to the system engineers who are trying to make a design that's effective and efficient, this design was very restrictive. And it made it hard during INT and less flexible if you have an issue once you launch and you want to send a ground command to close inhibits to see if you can make the system work. So it's difficult for troubleshooting. Because of this, GPM management decided to eliminate the safety inhibit unit box. Now the new design had inhibits, but these were now FETs on cards in different electronics boxes, and they were now initiated by safety critical software. Well, given what was decided on the SIU, the GPM safety team was asked if the new design was safe. It was our job to point out any inadequacies. So that's when I started to develop this method or technique. Now the conclusion we came to was the design with some tweaks could meet US and Japanese safety requirements. But now the inhibits we had were controlled by software. We did get agreement from systems and management that our new design included safety critical software. Software safety became one of the focuses we needed to have addressed on GPM. And so a software safety engineer was hired for our program. Okay. So before I go any further, I'd like to go over some terms. The first two I've actually talked about, inhibits and controls, but this is a block diagram of the GPM RF electronics box for the high gain antenna. You'll notice, let's see, I'll do another click here, like here, okay. I want to make sure we define inhibits. It's an independent and verifiable mechanical or electrical device that prevents a hazardous event from occurring. So the device has direct control and is not a monitor of such a device. So the examples in this block diagram are the green circles, the 1, 2, and 3. You'll notice that they are physical interrupts between power and function. Okay, the next definition that we have is control, which is hardware or software that affects the operation of inhibit. And that would include these tan circles that you see. Okay. Next is safety critical software commands. That's a command that either removes and or activates a safety inhibit to create a hazardous condition. So those would be, as an example, the 3 yellow arrows you see that have hazardous ground commands that are sent or initiated and then sent to activate each of the 3 inhibits. Now, drawn here, the inhibits are drawn as relays, but on GPM, as I mentioned before, they're actually FETs. Okay. So the next definition is fault or failure tolerance. That's the ability to sustain a certain number of failures and still retain capabilities. Now, on GPM, the hazards that we had were considered catastrophic. Catastrophic hazards would be ones where it could cause serious injury or death, or significant damage to either hardware or the facility for high-priced items. For GPM, if you're a catastrophic hazard, you need to be 2 fault tolerant or have 3 inhibits, therefore pointing out the 3 green circles again. So to be 2 fault tolerant, you need to have at least 3 inhibits in place, because if 2 of them fail, you have 1 remaining. Okay, and the last definition is designed for minimum risk. This is the method by which structural members, pressure vessels, pressure lines, pyrotechnics, material capability, mechanisms, where fault-tolerant design is not practically possible, shall be controlled by design standards and so forth. And I'll point out that under that umbrella is safe by design. There are situations when you need to contain a hazard And so you can't count fault tolerance quite the same way. One example would be, for instance, an arming plug. When you remove an arming plug, you're safe by design because the continuity of the circuit has been removed. Okay, next slide. Let's talk about GPM. What does it do and how many instruments are there? GPM stands for Global Precipitation Measurement, and it was launched February of this year, and it can measure ice, snow, and a mixture of conditions all around the globe. It has two instruments, DPR, which is dual precipitation radar, and it basically has a dual frequency transmitter receivers, and the instrument was designed by the Japanese. In addition, we have the GMI instrument, which is the GPM microwave imager, which was developed by Ball Aerospace in the US. There we go. Okay, so this is a view of what GPM looks like. This is in the stow position. These are solar arrays that are stowed. We have an HGAS, that stands for high gain antenna system, stowed, and the GMI instrument in stow position. The next view shows it deployed. You can see the solar arrays, high gain antenna is now vertical, and GMI reflector is also deployed, and the drum of GMI also turns. Okay, and here's the reverse side of GPM as well. So the order of activation is that, of course, the Omni antennas come on first after fairing is released, but before the launch vehicle separation. So there's an automatic sequence that goes with starting up the Omni antennas. After launch vehicle separation, the solar arrays extend out, and again, that's an automatic flight software sequence. Then, when the Omnis sync up to the ground, a ground command is sent to deploy the high gain antenna, and then it's turned on, so we switch over from Omni to high gain. Then the propulsion system initiates, and then the instruments start turning on. KAPR and KUPR are the two parts of DPR, so they turn on the radar, and then the microwave instrument GMI deploys and also turns on as well. So the next slide shows the instruments in action. So you can see the combination of readings that GMI gets from making their swath at an angle, combined with the DPR information that's gathered, taking their swath, looking at precipitation. That combined effort gives weather conditions at different heights of the Earth. And again, GMI only has a receiver, and the KAUPR have a transmitter and receivers. Okay, so we're going to have a little bit of audience participation here. Okay, so I'd like to ask you, what are the hazards that GPM has? I'll put a picture back up so that you can remember what it looks like. Okay, a little spin there. Particularly, hazards controlled by software of electrical inhibits. So, anybody want to shout out an answer? Solar array deployment. Thank you, Chad. So one of the hazards that we have is solar array deployment. Now, solar arrays are supposed to deploy after launch vehicle separation. That's not the hazard. The hazard, of course, is inadvertent deployment when we don't want them to deploy. So that might be at Goddard Space Flight Center when we're doing testing, or if we don't have ground support equipment hooked up to it while we deploy, that's a concern for the solar array for its safety. For instance, the solar array, the GMI, and HGAS are all designed to deploy in 0G. They're not designed to deploy in 1G. So what's another one? Yes. GNC? Well, GNC is part of the answer. I'll help you with that. Maybe propulsion system. Good, okay. Yes, propulsion system is, we have other components to GNC as well as propulsion, but yeah, propulsion has inhibits as well because we don't want the latch valves and the thrusters to open prematurely as well. Any other ones? Yes. Okay, I had transmitters, and I heard radiating the high gain antenna. Yes, basically the omni and the high gain antenna radiating at the wrong time. What about, we have two more deployments to talk about. What about those? The high gain antenna and also GMI as well. Because personnel could be injured. You could also injure the instrument if you don't have the proper GSE connected. And the other one would be the DPR instrument. That's radar. It's pulsed, but it has a lot of energy stored. Okay? So we came up with, in total, thank you for your help, six bullets here. List the 6 hazards that are related to software controls for GPM. So for each one of these bullets, I created a separate timeline chart to track safety inhibits and controls. Okay. Because of the limit of time, I'm only going to go over the 2 that are in red here. That's the solar array and the H-gas. Okay. So here's where we are in the agenda. Now I'm going to go through step 1 through 4. Okay. Okay. So this is what a safety inhibit timeline chart looks like. And I realize it's hard to see. This is just giving you the big picture. This is one of the end results for the assessments for GPM for H-gas deployment. As I mentioned, there's separate timeline charts for each of the 6 hazards, and we're only going to go through 2 today. So step 1 is to define the inhibits and controls, and we record that on the x-axis. Okay. Step 2 is to define the INT tests. Now you'll see a colored bar at the top right here. Okay, so the blue bar is the INT testing at Goddard. And you see that a large proportion of those tests are at Goddard. This one column, which is in purple, that's transportation to the Tanegashima range. And then the aqua color is the operations at the Tanegashima range. And then the beige right here is post-launch. Okay? So basically, you get your list of tests from the INT group, and then you try to develop this chart. And then the next step, and this requires teamwork and working together with INT and the systems folks and management on, well, given the inhibits we have in place and the testing, what position, what conditions are my inhibits in? So I chose to use green and red. Green to me means good, that an inhibit's in place and is functioning. Red means an inhibit's been removed. And you'll see a combination of color there because during certain INT tests, you have to remove inhibits in order to test them. But yet you still want to be safe. And that's the whole purpose of putting this visual tool together. Now there is a 4th step, and it's determining software criticality. And I want to go through that as we go along. By the way, formally, this chart is called the Safety Inhibit Timeline Tool. But it was affectionately known on GPM as the Christmas charts because of all the red and green and silver on it. So, okay, so let's start step 1. Okay, so this is the H-gas in the stow position. In order to stow the H-gas, there are 3 LRMs, which is launch restraint mechanisms. Okay, I'm going to go to the next slide. For each of those launch restraint mechanisms, they had 3 separate electrical inhibits. So let's go through this. So those electrical inhibits are shown in green. I'll mention that both for the solar array and H-gas, their inhibits are considered independent because the inhibits are controlled by different FPGAs. You can see them shown here. You can't see it on here, but all the inhibits are on separate cards, and they have separate controls as well. Okay, inhibits 2 and 3 are controlled by ground commands. And Inhibit 1 is actually activated by flight software after separation from the launch vehicle. Now, originally, the plan was to have all 3 inhibits to be activated as ground commands. But what happened was when we eliminated the SI unit, we started running out of real estate in the different boxes, the PSC, DFU, and there's a couple other boxes, electronics boxes that hold these inhibits. Started running out of real estate. So we had to double up on the inhibits, the FETs. But so the systems engineer came and talked to us, and they said, they asked us if it was okay if they could double up inhibit number 1 for the solar array with the high gain antenna. And that inhibit would then deploy after flight software, almost 9 minutes after separation. Well, at first we thought, well, yeah, that's not a problem. I'm concerned about design up until flight separation from the launch vehicle. And you're talking about 9 minutes past that. I'm good with that. Why not have inhibit number 1 be shared? But what I was thinking about was orbit. I wasn't thinking at the moment about INT at Goddard. What happens to the high gain antenna, inhibit number 1, when you decide that you're going to deploy the solar arrays to do a test, and you want to keep the high gain antenna stowed? What happens to inhibit number 1? It gets removed. Are you too fault tolerant? Do you have 3 inhibits anymore? No. So that wasn't obvious to us until we started designing the inhibit timeline charts. Okay, before we leave this chart, I'm going to mention that we also have arming plugs to keep us safe. And that's the answer that comes out of this, that during solar array testing, we would need to make sure that arming plugs were removed on H-gas. Okay. Also, in some tests, we actually remove the NEAs to do testing. And both removing arming plugs and removing NEAs isn't really fault tolerance. That's really being safe by design. And I mentioned that just like I have inhibits shown here in green, there's also a redundant set shown in the redundant boxes as well. So GPM was a fully cross-strapped system. Okay, so here's a summary of what we just talked about. So H-gas, high gain antenna, has 3 LRMs, 3 deployable hinges. Electrically, they are by design 2 fault tolerant. We had those 3 green circles, you remember. And then these are all the inhibits I can count, okay? I had 1 FET I could show in the power systems electronics. I had 2 more in the deployment firing unit. They're all independent. In some cases, when I have a test where the power's off to the spacecraft, I can count a 4th inhibit as well. That's only when the spacecraft's unpowered. In addition, we had a strap that went around the high gain antenna when it was in stow position. So that strap or tie, we also included as an inhibit. We talked about arming plugs being removed. We talked about NEAs being removed. Another item was keep out sign. This technically is not an inhibit, but it is a control. Okay. So this is an important list. So this is step 1 of the safety inhibit timeline tool by defining all the inhibits. So this is where the information goes right here. And I promised you I would blow it up so you could read it better. Okay. So you can see column number 1 basically is the inhibits we had on the previous chart. I added 2 more columns, the inhibit types that we have, and also how the inhibits are controlled. Remember we said that inhibit number 1 was flight software, and inhibits number 2 and 3 were controlled by ground commands over the 1553 bus. I would mention that some of the remaining inhibits are controlled by INT procedures. This is important as well. Part of my job is to look at all the hazardous INT operation procedures. So this made my job easier. If I saw that a particular test needed to have a safety strap in place, when I'm presented with that procedure to review, I'll make sure that there's a line and a sign off, and we have our quality engineers sign off that they see that strap is in place for the testing. So this made my job easier. It made sure that I understood what I needed to do to meet that requirement. Okay, so now we're going to talk about step 1 for the solar arrays. And I'm going to go through this a little quicker because it's very similar to the high gain antennas in the sense that it also has launch restraining mechanisms, but in this case it has 5. But they're initiated by flight software. Inhibit number 1 is removed by separation switches with the time delay of 8 minutes and 56 seconds. In this case, inhibit number 1, again, is tied to the H-gas, so it is the same. But inhibit number 2 and 3 go off of launch vehicle brake wire separation with an added delay of 10 minutes and 5 seconds for inhibit 2 and 10 minutes and 25 seconds for inhibit 3. And likewise, the same holds true about independence of inhibits. We have redundancy, we have the safe in arms, and NEAs during some testing is also removed. Okay, so this is our summary chart, and what's different for the solar arrays is accented in red here. 5 mechanisms. Inhibits are similar, except we use a tether pin retaining system rather than a strap. So basically, this is step 1 for the solar arrays, and would again go on the timeline chart. So we're ready to move on to step 2, which is defining the INT tests. Okay. So the left-hand column are a list of performance tests, and the right-hand column is a list of environmental tests. So the first test we have up there is CPT comprehensive performance test. The goal of observatory CPT is to fully check out the observatory in all its operational modes in as many configurations as possible. That's A side, B side, and also cross-strapping configuration. CPT verifies all copper paths and configurations. For GPM, CPT took 24 hours for 8 days. Where possible, many of the various GPM components and instruments were tested simultaneously. The next test was functional testing, and basically that's a subset of CPT. It tests all copper paths. It looks at side A and B, but doesn't look at cross-strapping. And the time allocation for this test is much more limited than CPT. The third one is aliveness tests. This is basically to turn on all components, but only verifies a few key components like voltage and current. And it also tests A and B side, but there's no cross-strapping again. Alignment, and that's usually for the radar and microwave, for their output pulses and receivers, but also for the alignment of the propulsion thrusters as well. Mass properties, that's the total mass, center of gravity, and moment of inertia, about 3 axes. This is among the characteristics that are calculated during the design process. Since the correct control and guidance of the spacecraft depends on the accurate knowledge of these values, they are subsequently measured as part of the test campaign. So the spacecraft is spun on a Miller table, and they do rotational inertia checks, much like tire balancing. The table is close to frictionless surface, and it rotates, and the spin table measures wobble, and small weights are added on to balance off the wobble, and that's how you control your center of gravity. The next test is magnetic survey. The GPM has torque bars and 3-axis magnetometers, which are sensitive to magnetic sources. So there's an instrument level, spacecraft level, and observatory level testing that's done for magnetics. And so in this test, you have to be in your final launch configuration. So in this case, arming plugs need to be put in, any safety straps need to be removed. So that kind of dictates the configuration of the spacecraft. The next test is end-to-end and mock testing. That goes hand in hand, and basically it's a CPT test, except that the controls are through the mock interface with TDRS. Usually there's a launch timeline that's being simulated. We needed to make sure that this simulation, say of solar array deployment, didn't really deploy the solar arrays unintentionally. So we wanted to make sure we were just simulating it. And then we also had deployment and stow that was done. This is where we wanted to deploy, say, the solar arrays. So special GSE had to be used and attached to the solar arrays. And then the non-explosive actuators were fired after the 3 inhibits were removed. Next test is walkout test, where, again, the solar arrays, say, would be walked out. The inhibits are still in place. The non-explosive actuators are not fired, but they want the solar arrays to be extended. And of course, the GSE is also used for that. Okay. Okay, so now this shows you 3 different configurations here. This is a flight configuration, say for a deployment circuit. You can see the arming plug shown here, and you can see the continuity of the circuit through here. It goes through the NEA and down through another inhibit and out to ground. During observatory functional testing, you'll notice that the arming plug is removed. And what's put in place is a testing plug where the NEA simulator can then be installed, and that, of course, that tests your copper path. But you'll notice that when that's done, that the circuit is no longer completed. And again, the point here is to show you that during some of this testing, you're safe by design when you're in that configuration. And the same when the NEA is removed and you attach the NEA into where the NEA simulator into where the NEA was. And that's done during CPT testing. Okay, so going back to this chart, we have environmental testing to talk about as well. So these simulate launch in space environments such as shock separation and spacecraft thermal environment. So performance tests that are listed in the left-hand column are inserted in between the environmental tests and sometimes in different configurations as well. So thermal back testing is done in a thermal back chamber. EMI testing is done in an anechoic chamber. And during the EMI testing, we're testing self-compatibility, but we're also testing compatibility with the launch vehicle limits. There's a specialized signal injection test. This was for the DPR instrument. That's where they were testing their receivers. And this test was done not only at Goddard, but also at the range as well. So these performance tests are repeated at the range, but the environmental tests, with the exception of signal injection, are only performed at Goddard Space Flight Center. So the next slide is a list of all the GPM tests and events in order, starting with integration all the way through launch vehicle separation. The ones that are noted in red, those are the environmental tests. Those that are in bold black are the performance tests. Purple right here is the transportation to the launch site. So you can see where that takes place. So this is the completion of step 2. Getting this list together took a lot of time and effort working with our INT group and GPM management. In addition, the systems engineer reviewed this list as well to make sure it met all the testing objectives. So after you have this order, you now have step 2 of the Christmas charts completed. Okay, so now let's move on to step 3. Step 3 is determining which inhibits and controls are in place during each of these tests. And we need to have multiple meetings and involve safety, INT, and systems to determine what was being tested during each of these tests and what configuration the inhibits were in. And then it got documented on the Christmas chart. So looking at this early example, this is the Christmas chart prior to adding on software safety assessment. And again, the x-axis we just talked about were the safety inhibits for the high gain antenna, and the y-axis are all the testing that happened. And by our definition, green is good, so an inhibit's in place and keeping you safe. Red means an inhibit's been removed, and you can't count it for keeping the system safe. So to make sure everybody understands, these top three inhibits are the electrical inhibits controlled by software. So when the three are green, they're in place. When they're red, the software has sent a command to the inhibits to have them close. Another example would be, this is the row for the arming plug. So when the arming plug shows green for any of these tests, that means the arming plug has been removed, so you're safe. If it's red, the arming plug has been installed, and you cannot count it in your system for inhibits. And the same with the NEA as well. You can see the NEA only during certain CPT tests is ever removed anyway. And this is spacecraft power. So whenever power is removed during testing, or it's an unpowered test, again, we add it as another inhibit, so it's green. If you have a powered test, it shows up as red. And then below, we put it as a separation, keep out zones, because it's really not an inhibit, it's more of a control. So let me click on here. Okay, so you can see, remember we talked about that inhibit number 1 for the solar array and H-gas are ganged together now. So this column, and you can see 2 others here, are talking about solar array deployment. So you can see one of those inhibits was removed. And so once I discovered that, I had a meeting with systems engineers, and I pointed out, I said, you know, we don't have fault tolerance here unless we go ahead and remove the arming plug and maybe have also a keep out zone doing solar array testing. And they all agreed. They said, oh yeah, you're right, we have to have that arming plug removed. But when it came time for me to review the procedure for the solar array test, there wasn't a step in the procedure to make sure that the H-gas arming plug was removed. Okay? And I made a comment to the person who wrote the procedure, and she came back to me and said, Shirley, this is a solar array test. Why do we have to worry about the high gain antenna arming plug being removed? So then I realized at that point that the systems folks hadn't told the INT folks, or at least not the person writing the procedure, that those 2 inhibits were coupled together. So then we immediately had a meeting, and I had this timeline chart there, and we were able very quickly to point out what the issue was, and very quickly come to the conclusion that yes, we needed the arming plug removed. Even though it wasn't part of the solar array test, it was important to maintain safety for the H-gas. So I found it to be a communication tool to help me work with all parties on GPM. Now, another thing I wanted to point out on this chart is you can't count the 3 electrical inhibits. You can see it's red. But of course, we have the arming plug removed and also the safety strap on. This is one of our tests. This is the, I believe, functional test. Next thing, point out, that's the CPT test. You can see the inhibits are removed except for the NEA. Once we remove the NEA, it's safe by design, even though you only count 1. So there's a mixed philosophy here. In some cases, we're counting fault tolerance because we have those 3 electrical inhibits in place. And other times, we're looking at, say, by design or design for minimum risk. Okay, and the last item, well, here we're deploying, boy, all the inhibits get removed. Well, we have to have the proper GSE attached, and we do, as best we can, have a keep out zone, and everybody in the area is aware that we're doing a deployment. Okay? Okay, so you would think since the inhibits for H-gas were very similar to solar array that the timeline charts would be very similar. But you'll notice that there's a lot of white and it says NA in all these columns. That's because during these particular tests, the solar arrays were removed. Okay, so during thermal vac and during EMI tests, we didn't have the solar arrays attached. They were attached for things like vibration acoustics and shock separation, but then removed later for certain other tests as well. So that's what that chart looked like. So now let's start talking about step 4. So, okay, so after the SIU electronics box design was removed and the project agreed that we had safety critical software, they really didn't know what that meant and the level of scrutiny we needed to have for our software. Systems was concerned that they did not want to have the software safety reviews and oversight to slow things down. Meanwhile, system safety and software safety folks took a different, more conservative approach. We wanted to review everything, witness every test that's listed in that Christmas chart. So that's at 49 tests, right? So we were taking the strictest interpretation of NASA standard 8719.13b. But at the same time, we sort of agreed that our approach might be unreasonable, and we would need an army of software safety and system safety people to witness all these tests. So GPM, by the way, during INT, ran for over a year, 24/7. Okay, and sometimes we had as many as 3 hazardous operations going on at one time. So schedule was an issue, and it was a very complex system. So software safety engineer was tasked to determine the most important times for software safety to be involved. I'll mention Charlie Rogers was our software safety engineer, and he had an idea to address software safety the same way we did the inhibits and controls on the timeline. He asked me, was there a way to include software safety on the Christmas charts? So I guess he saw that we were able to get everyone to work together by using these Christmas charts and understanding what inhibits we had for testing. And he wanted to have that same approach for software safety. So I agreed to add that on the chart. So GPM safety, software safety, systems engineers, managers, INT all sat down and discussed what a reasonable approach would be for software safety. And that became step 4. We came to an agreement that if 3 inhibits are in place, controlled by software, so that would be the top 3 here, if they're green, because they're in place, and if the spacecraft is powered, so that means that in this column, spacecraft power would be red, because that inhibit's been removed. Then software was involved in safety. So basically, let me see if I can do this. So we'll go through it here. So here we have three green inhibits, and then the spacecraft is powered, so it's red. But in this case, we have some additional inhibits, like the arming plug is removed and the safety straps are in place. So it was decided that yes, software was involved, but it wasn't as critical as this case. This is during acoustics testing, where we have 3 inhibits in place, we're powered, and then there's no additional inhibits. So we had a green X in place. So this row, by the way, is the step 4 part. By the way, if you have a mission that had no safety critical software, this row would be very boring. It basically would be all silver. There would be no green X's, no green slashes. Okay, so the significance here is we have safety critical software. So what that means is that we can look at the Christmas charts, and you can see that there are times when it's more or less important to involve safety with respect to software. So there are a total of 49 tests or events across this chart, but 7 of them become software safety critical. That's less than 15% of these tests. Systems felt this was a reasonable list of tests that were safety critical. I believe also that the software safety engineer was able to review any test he wanted to, but in the case where there were X's on them, he was a required reviewer, and he was required to witness the test as well. Now, in the case where we have some columns that are slashes, it was my responsibility to make sure those extra inhibits that we needed in place, making sure the arming plugs were moved, making sure the straps in place, that those get written into the procedure, and that we had a quality or safety sign-off that they actually happened, okay? I'll also mention that you'll notice that there's more X's as we get closer to launch. These are basically the last hours just before we launch and also post-launch. That's when you're in launch configurations. A number of inhibits have to be removed. You have to have your arming plugs in place. And in some cases, you have power test. Okay, so this is it for solar arrays. And it's very similar as well, so I'll go through this real quickly. Green inhibits in place. In this case, we're powered up. The example here is vibration and acoustics testing. And of course, those are X tests. And the example here would be a functional test. And of course, we have the other inhibits of removing arming plugs. And that's why that's a slash. So for this, there's a total, again, 7 critical software events, and 4 which have slashes. Okay. Okay, so remember we talked that there are actually 6 timeline inhibit charts. I presented 2 in detail. I'm just going to quickly, for completeness, go over the other 4. So this is for GMI, okay? GMI, basically it's similar. It's another deployment. One thing that is unique about GMI is inhibit number 1 that we count for GMI is power to the instrument. So every time we did an aliveness test, we had to remove inhibit number 1, okay? So you notice that inhibit number 1 shows removed several times. So we had a meeting, and I pointed that out to them, and they said, well, can we count the fact that we have software that has to be in a particular mode before we can deploy? And so I've added that onto the Christmas chart as well, that GMI has to be in deployment mode in order for it to actually deploy. So we were able to add on another inhibit and in most cases be 2-fault tolerant. You will notice that it has more X's than some of the other charts. That's because it didn't have a safety trap. And and next one is the RF transmitter. And the philosophy for the RF transmitter is that either you have the hat coupler on while you transmit, or basically you have the inhibits in place. So you see an alternation between red inhibits here and green, and red here and green up there. The only exception to that would be during EMI testing, when you need the hat coupler removed and you need to remove the electrical inhibits to do the testing. But in that case, you have a keep-out zone, which is basically containment of your RF during that testing. And then the other time is post-launch, when you want the RF to come on. And here you have, 6 green X's as well when software is safety critical. For DPR, we had that test we talked about called signal injection. During that test, we needed to test the receivers. But in order to do that, we had to remove their inhibits 1, 2, and 3. So they told us that they had another inhibit as well. Apparently, there's another set of FETs that should be included. So we added another row for them. But that still didn't give us enough inhibits. We also had an RF absorber. And that's really not an inhibit. It reduces the severity, maybe, of the RF because it's absorbed, but it's not really inhibited. So I got the systems folks to agree, and the instrument manager to agree, that we needed to add one more inhibit in, which was an RF detector. And the way it works is, if the DPR instrument had gone off inadvertently, this RF detector, which needed to be put right near the KAPR and KUPR, and it would detect the radar. It would immediately send a signal to our ground support equipment that would shut off the transmitters for DPR. And we also agreed that during the signal injection test, we would maintain a keep-out zone. And there again, it has a combination of times when software is critical as well. Oh, and the last one is propulsion. Now, propulsion, there's a lot of NAs there. And the reason why is you don't fill your propulsion system with hydrazine until you're just about ready to launch. And that helps you to be very safe. So basically, the system is filled, then the fairing goes on, it's lifted onto the rocket. There are a couple tests that are done at the Japanese VAB and also at the pad, and then from there on, it's launched. Now, something I didn't mention, and I should, for all these X's here, we also have the option of putting them on a prohibited command list. What that does for us is, if we don't want to have a deployment or an opening of a valve or so forth, we can put it on a prohibited command list, and if the GSC sees that that command is initiated, it will not let it go through. Okay, so that's another safety feature you have to have for safety critical software. Okay, I'm probably running low on time. Okay, I got another minute or two, my last bullet is about unique hazard reports controls for software. And I want to credit Charlie Rogers, because this information came directly out of the GPM hazard reports, and he was the developer of all of our software safety information. Basically, hazard reports are provided to the range to describe what can cause a hazard, control a hazard, and verify controls of a hazard. Special additional verifications were added to the GPM hazard reports that were only required because we had safety critical software, those X's you saw on the chart. So I'm just going to hit the highlights here. Basically, we made sure that for our safety critical software, no more than one safety critical command in an onboard script, or RTS, could be sent at one time. Only one inhibit could be removed for each ground command. So we had 3 separate ground commands for 3 separate inhibits. All hazardous commands required 2-step commands. So they had an initial activation and then a confirmation. For any hazardous operation at Goddard or at the launch site that was not supposed to happen, there was a way to make it disabled by putting on the prohibited command list. And that rendered it temporarily disabled. After fueling and after pad testing, thrusters and latch valves opening were on the prohibited command list until right before launch. Okay. Okay, so now I have summary. Okay, so in summary, what I've learned from this is that INT is complicated in terms of INT inhibit controls during individual tests. A system that we generally think of as 2 fault tolerant because it has 3 electrical inhibits. may need to remove inhibits during testing. So during INT, there's more of a mixed philosophy on how to make something safe. You have a combination of fault tolerance along with design for minimum risk. And also, next. Software was not always considered critical, even though we had safety critical software. So we were able to focus with this tool on the more safety critical areas for software. The tool helped safety bridge a gap of understanding and understood the INT planning. It allowed us, as a safety team, to make well-informed decisions, especially when reviewing procedures. It was a time saving for me because I could look at a procedure and kind of read it, but then I could go back to the Inhibit charts and determine what are the key components I needed to see in that procedure. It also was an excellent communication tool with our systems engineers and project managers. I was able to point out some inconsistencies, potential risks, and hazards. And this tool can be used on other missions as well. I'd like to thank all the several groups with this project. Of course, GPM, NASA, JAXA, my company, ASRC, and Ares are prime as well as embedded flight systems. Are there any questions? Do we have time? Oh, okay. Oh, I took the microphone away. Oh, no.
Just a quick question procedurally. I had noticed when you were looking at one of the safety straps, you had just, instead of going forward with the testing, you said, okay, we control that procedurally, which is something I've seen in my field as well. A lot of times with the documentation, though, I'm FDA regulated. If we had to go back a little bit later, you gave another example where there was coupling, and you had to go back to that engineer and update that procedure. A lot of times, if we reference our procedure it has to be the latest version, and we have to capture the version and say anything. Some places will let me get away with anything subsequent after, but that procedure has to be signed off and locked down before I can sign off and lock down my validation. And I'm just curious, is that the case here, or is it a little bit more wiggle room where you could go back and forth a little bit on it?
Well, ideally, somebody writes the procedure, gives you enough time to review it and make comments. And anytime you make a comment and anytime a change is made to the procedure, then everybody who's on the list of required reviewers has to re-review the procedure. So there is supposed to be wiggle room that we get the procedure several days in advance to review it and then turn it around with comments. And usually, like for CPT testing, we did CPT testing several times. So the first time we did CPT testing, it took several weeks before that procedure was approved. Not just from safety, but also from systems as well. There were certain tests that had to be added in, and maybe they changed the sequence here and there. And so every time you make a change like that, the whole group had to go back and review the latest version. And that's why we need to review it as early as possible.
Thank you.
Thank you.
I'm just curious if other projects have shown interest in this kind of approach towards Christmas charts approach towards safety during each aspect of test during up to launch.
So GPM was the first. There is one other program at Goddard who is looking at a modified version of the Christmas charts. It's a less complicated spacecraft, and they're going to use a modified version of it. But my intention is the next project I get on. Right now I'm on Discover, and I got on it pretty late. It's getting ready to launch in January. That's not when you want to start this process. So, so I'm hoping that the next mission I work on, maybe we can include that as well. Thank you very much. Arigato gozaimasu.